Welcome to the Deep Dive, the show where we distill complex research into surprising, actionable knowledge, custom tailored for you. Today, I want you to picture something that's becoming, well, increasingly common. Think about an autonomous drone zipping through a city skyline, dropping off a package precisely where it needs to go. While just below, maybe a high-speed train is racing across the landscape, passengers inside seamlessly streaming movies, and at the exact same time, maybe in an apartment building nearby, someone's completely immersed in a virtual reality experience, totally stationary. Now, all these devices, they demand instant, reliable wireless communication. But here's the rub, right? They're moving at Today we're embarking on a deep dive into a really groundbreaking piece of research. It's titled Modulation Classification of OTFS-NOMA in Heterogeneous Mobility Profile. It's a paper by Pawan Maurya, Kamal Captain, Shrinkar Mar, and Prashant Keshav. And honestly, this isn't just some incremental step. This research tackles a truly critical challenge right at the frontier of wireless communication. It's asking, how can our communication systems intelligently adapt to users with radically different movement speeds? Think the high-speed drone and the static VR headset, and specifically, how do they automatically figure out what kind of signal is being sent from each one, even when those signals are essentially made?
Deep dive is really all about pushing the boundaries of wireless efficiency and reliability. We're looking at future where our networks need to be incredibly flexible. They need to support scenarios where some users are literally traveling at hundreds of miles per hour, experiencing rapid and unpredictable signal changes, while others are rooted firmly in place. So we'll explore the ingenious underlying technologies that make this possible, the clever problem solving involved in separating these complex signals, and critically how machine learning is stepping in
as the sort of intelligent brain to make it all work seamlessly and automatically. It's a fascinating look, really, at how our devices will talk to each other in the next generation of wireless.
So let's begin our journey by pinpointing the core problem that this paper really aims to solve: wireless communication in motion. Specifically, why are fast-moving objects like that high-speed train we mentioned, or a commercial drone, or even just someone jogging with their smartphone, why are they so incredibly challenging for traditional wireless systems? It feels like we're constantly upgrading, 5G, 6G on the horizon, promising ubiquitous connectivity, yet high-speed mobility remains this persistent thorn in the side. Why is that?
Yeah, that's a really fundamental question. Something engineers have wrestled with for, decades. The core issue, especially with these high mobility users, is something called the Doppler effect. Think about an ambulance siren, right? As it approaches you, the pitch sounds higher, and as it moves away, the pitch drops. That change in pitch, that's the Doppler effect. It happens because the frequency of the sound wave shifts relative to you. In wireless communication, the exact same principle applies to radio waves. So when a transmitter or receiver, or maybe both,
are in rapid motion relative to each other, the frequency of the received signal undergoes this rapid continuous shift. And this isn't just a minor annoyance. These rapid changes
trying to have a perfectly clear conversation with someone shouting from a car speeding by at 100 miles an hour. The words get distorted, dismirrored, sometimes completely lost. The channel conditions are just changing so quickly that the system can't adapt fast enough. It fundamentally breaks down.
Okay, so that makes perfect sense. That Doppler distortion is a huge hurdle. So how do you mitigate that kind of severe distortion and instability? This is where the paper introduces a truly innovative technology, positioning it almost like a hero for these high mobility scenarios. Orthogonal Time Frequency Space, or OTFS. Conceptually, what is OTFS? How does it manage to handle movement so much better than the more traditional methods we're used to?
Well, what's really fascinating here is that OTFS isn't just an incremental improvement. It's not just a slightly better version of what we had. It represents a fundamental paradigm shift in how wireless signals are processed and organized. It's a whole new way of thinking. See, traditional wireless systems,
dynamic, unpredictable, chaotic even. OTFS takes a radically different approach. The paper states it's particularly proposed for challenging communication scenarios.
Multiple echoes or multipath components, right? Each arriving with a slightly different delay. And as we just discussed, if you're moving fast, each of those echoes will also experience a different frequency shift because of the Doppler effect. The delayed Doppler plane in OTFS, it explicitly captures and processes these two key dimensions, the time delays of all those reflections and the Doppler shifts caused by motion. By transforming the signal into this domain, the wireless channel, which would otherwise appear wildly unstable and time-varying due to speed, it transforms into something much more
Predictable and stable. Essentially, it becomes a nearly time-invariant channel from the signal's perspective. This inherent stability makes it far, far easier to estimate the channel, process the signal.
Okay, wow, so OTFS sounds like it brilliantly handles the speed aspect, really taming the chaos of these high mobility environments. But in our incredibly dense modern world, it's not just about speed, is it? It's also about efficiently packing more and more users onto the same finite network resources. And this is where another crucial technology enters the picture, NOMA, or Non-Orthogonal Multiple Access. So if OTFS handles speed, NOMA seems to handle the efficiency and user density side of things. What's the core idea of NOMA? Why is this concept of sharing is caring
so crucial and, frankly, revolutionary here?
Yeah, NOMA is all about maximizing spectral efficiency. That's the key metric. How much data you can transmit over a given amount of radio spectrum. It's precious stuff. Traditional multiple access schemes like OFDMA, which underlies a lot of 4G LTE and even parts of 5G, they typically ensure that each user gets their own distinct orthogonal slice. A slice of radio spectrum or time, or maybe a unique code. The point is, they don't overlap, they stay in their own lanes. But NOMA, it basically throws that conventional
Wisdom out the window. Its fundamental principle is allowing for simultaneous data transmission to numerous users over the same resources. That's the big change. This means multiple users can
really critical consideration. This efficiency comes at a cost.
There's always a trade-off, isn't there?
Always. It inherently introduces co-channel interference because everyone is sharing the same resources. You can't avoid it. It's a deliberate trade-off, though, a carefully managed interference. But it's one that's increasingly necessary to support the sheer density of connected devices we now have. From smartphones to countless IoT sensors, all clamoring for bandwidth.
Okay, so let's connect the dots. If OTFS is specifically designed to conquer the challenges of high speed, and NOMA is designed to maximize efficiency
By letting many users share the same resources. What happens when you combine these two powerful technologies? This is where the core proposition of the paper gets really interesting, because it's specific.
This concept of heterogeneous mobility is precisely what makes OTFS-NOMA so compelling. It addresses a very real-world dilemma for future networks. It simply means you have a mix of users with wildly different movement patterns, and as a consequence, vastly different wireless channel conditions, all trying to communicate on the same network at the same time. The paper wisely categorizes these into two main types: far users and near users. Now, this isn't necessarily based on their physical distance,
but more on their effective channel conditions and their mobility. So the far users. These are defined as those experiencing challenging channel conditions, primarily due to their high mobility.
power for the fast movers. Got it.
Exactly. Then, in contrast, you have the new users. These are the low mobility or maybe completely static users. Your smart home sensor, your tablet streaming a movie while you're sitting still, or even just someone browsing on their phone at a coffee shop. They experience much more stable channel conditions, which gives them higher channel gain, meaning their signals are less attenuated, less weakened by the environment. Consequently, they are allocated low power. They don't need as much help. Now, the truly clever part of OTFS-NOMA is how these signals are actually combined and transmitted
in the power domain. This means both the high power signal for the far user and the low power signal for the near user share the same spectrum at the same time. But they are superimposed, layered on.
This precise power allocation is absolutely key to allowing both signals to coexist on the same resource block without completely clobbering each other.
Wow. So, by strategically allocating power based on mobility and leveraging these advanced technologies, OTFS-NOMA essentially creates a single combined signal. And this allows for remarkably effective adaptive modulation tailored to individual channel conditions. Is that right?
Exactly.
So the system can send signals to a fast-moving drone using one type of modulation, maybe something very robust, and to a stationary smart home device using another, perhaps more efficient modulation, all on the
very same slice of radio spectrum.
Precisely, without the interference being an unmanageable mess.
But this raises a crucial question for you, the listener. What does this all mean for a device trying to receive these?
Exactly. Imagine you're that near user, your smart home device maybe. You're receiving this single composite signal. The signal contains your own low power data, but it's completely mixed in with a much higher power signal intended for the far user, say, that drone, all on the same frequency. How do you, as the near user, possibly manage to separate your own signal from that dominant overlaid signal meant for someone else? It really does sound like trying to have two conversations in the same room at the same time. One person shouting,
the other whispering, and you only need to hear the whisper. How do you untangle that audio chaos?
That's a perfect analogy for the challenge they face. And the elegant solution employed here is called successive interference cancellation, or SI. It's a clever multi-step process that effectively peels back the layers of that combined signal, like an onion. The process works best like this. The near user initially decodes the far user signal from the received signal and then subtracts it. Remember, the far user signal is allocated higher power. That's key. It's designed to be more easily detectable, even in the presence of the weaker near user signal.
So once the near user successfully identifies and reconstructs the far user signal, it then computationally removes or subtracts that high power interference from the total received signal.
Okay, so it needs to know how the far user encoded its data.
Exactly. For instance, does the far user transmit its data using BPSK or QPSK or maybe 16QAM? These are different ways of encoding bits onto the radio wave. If the near user doesn't know the specific modulation scheme, it simply cannot accurately decode and subsequently subtract the far user's signal. The whole process falls apart. And obtaining this prior knowledge is described as challenging in real-world scenarios. It typically requires additional signaling or control channels just to
Inform the receiver, hey, the far user is using QPSK right now. But that introduces overhead. It eats into precious bandwidth and adds latency. And that overhead is exactly what wireless...
Right, you want the network to be as efficient as possible, and this is precisely where automatic modulation classification, or AMC, comes to the rescue, isn't it? The idea is that the system doesn't need to be explicitly told what modulation scheme is being used. It figures it out on its own, automatically. This ability to automatically identify the modulation scheme without that explicit signaling is what can reduce this overhead. It's like having an intelligent ear that recognizes different voices without needing to be introduced first.
Exactly right. And while
Automatic modulation classification, AMC, has been a field of intense study for, well, decades. Most prior work, like various likelihood-based approaches mentioned in the paper,
precisely, they were designed for situations where each user had their own dedicated slice of spectrum or time. Clean signals, relatively speaking. Crucially, these earlier methods were not built to handle the inherent co-channel interference that is absolutely fundamental to NOMA systems, where multiple users are intentionally sharing the same frequencies. Now, there have been a few existing AMC papers specifically for NOMA systems, some using cumulant-based methods or even deep learning, but these are still lifting from the specific and highly complex environment
created by the unique combination of OTFS and NOMA together. This raises the really important question that this paper courageously addresses. What about AMC specifically for the unique challenge?
And this is truly the groundbreaking contribution of this research, isn't it? The paper explicitly states, and I'll quote it again, "To the best of our knowledge, no work on AMC for OTFS-NOMA system is reported, making it a fresh field deserving of exploration." It's a pretty bold claim, almost a declaration of pioneering work. So from your perspective, what exactly makes this particular combination OTFS and NOMA so unexplored for AMC? Why was this gap there, and why is tackling this challenge such a critical step for the future of wireless?
Well, that statement isn't just academic modesty. It really underscores a very real technical void they're filling. Think about it. If you're building the next generation of wireless networks, say 6G and beyond, networks that need to seamlessly blend ultra-fast connections for autonomous vehicles with high-density IoT sensors with smart city infrastructure, you absolutely need both OTFS for its brilliant mobility handling and NOMA for its spectral efficiency. You need both. But here's the problem.
When you combine them, you create a signal environment that is fundamentally unlike what previous AMC methods were built to classify. It's a whole different beast. You have the complexity of the delay Doppler domain product.
Effectively saying, look, this powerful combination of OTFS and NOMA is coming, it's necessary, and we need a way to make it work intelligently. And secondly, and this is truly crucial for any machine learning-based approach they had to first generate the data set for the OTFS NOMA system. Why? Because no such comprehensive and realistic data set existed prior to their work. Zero.
They had to build the training ground from scratch.
Exactly. This is a massive undertaking, simulating literally millions of complex signals under all sorts of conditions, just to create a realistic and comprehensive training ground for their AI models. You simply can't train an AI without data, and in this cutting-edge area, they had to create their own. It's a huge contribution in itself. And then finally, after creating this unique data set, they proceed to extract relevant features from this highly complex data. These features, as we'll discuss, are the specific
characteristics of the signal that the machine learning models can actually latch onto and learn from. Then they train and rigorously assess the performance of various machine learning classifiers to identify
truly huge undertaking, starting right from the ground up by generating their own data. It really highlights the novelty. So let's dive into the nuts and bolts of how they actually built this intelligence. How do they do it? They started by setting up a very specific yet realistic simulation environment for their experiments. Can you walk us through what that setup looked like? Specifically, the communication scenario and the types of users they modeled.
Absolutely. Their work meticulously focuses on a downlink communication scenario, which means they're simulating signals transmitted from the central base station, basically our modern-day cell tower to the users. This is the most common direction for mobile communication, like streaming video or browsing. And to truly test the capabilities of OTFS-NOMA in these diverse environments, they designed their simulation to include two distinct users. And these users perfectly represent those heterogeneous mobility profiles we talked about earlier.
One user is modeled as a high mobility user. This is our FAR user from the earlier discussion. Because of its challenging and rapidly changing channel conditions due to speed, this user signal
modulation sends out this combined power domain multiplex signal intended for both users. We've talked conceptually about OTFS operating in this unique delay Doppler plane. That's where the magic happens for mobility. But how does the signal actually journey from that abstract plane within the base station, travel through the air, and then get processed inside the near user's receiver, finally becoming ready for the machine learning algorithm to analyze it? This sounds like a seriously complex, multi-stage transformation process.
It is indeed a fascinating and intricate journey, a complex dance of mathematical transformations, really. But they've broken it down systematically in the paper. Let's trace the signal.
Translates the unique OTFS signal from the delay Doppler domain into the more familiar time frequency plane. This results in signals like XF&M for the far user and XN&M for the near user. It's kind of like converting a special code into a format that more traditional radio systems can understand before you actually transmit it. Now in this time frequency plane, these two user signals are then superimposed in the power domain, just as we discussed earlier. This forms a single
combined signal, XN&M. This composite signal then takes another step through something called a Heisenberg transform. This transform converts the signal from the time frequency domain into a pure OTFS modulation to prepare for analysis. First, it goes through a Booknote transform, which is essentially the mathematical inverse of that Heisenberg transform we mentioned earlier. This converts the received signal back to the time frequency domain, yielding Y in LM. Then there's one final step, a simplex.
Machine learning algorithm will then analyze to classify the far user's modulation type. What is truly impressive here is how they meticulously prepare this intricate multi-domain signal, accounting for real-world channel effects like fading and noise, and deliver it in a standardized format that's perfectly suited for artificial intelligence to interpret. It's quite an elegant processing chain.
That is a seriously intricate and multi-layered process, wow. But your breakdown makes it really clear why each transformation is necessary to get it into that final analyzable state. And then, as you mentioned earlier, the absolute necessity, they had to create their own data set for this. Given that no such data set existed for OTFS-NOMA AMC, generating such a comprehensive training ground for their AI must have been a truly monumental task. What were the specific parameters and the sheer scale of this custom-built data set? And why were those particular choices so important for the research?
Well, the custom data set was, without exaggeration, a foundational pillar of their entire research. It really was a massive undertaking. And it was meticulously simulated to capture the full complexity and variety of the OTFS-NOMA environment. They generated this data set by essentially recording that complex signal, YK, at the near user receiver, across a huge range of realistic and challenging scenarios. To make sure the data set was truly representative, they considered common and crucial modulation types for both the far and near users. Specifically,
BPSK, binary phase shift keying, QPSK, quadrature phase shift keying, 8PSK, 8 phase shift keying, and 16QAM, 16 quadrature amplitude modulation.
transmitted signal lengths, where n equals m, specifically 32 by 32 and 64 by 64 grids in the delayed Doppler domain. This allows them to rigorously test how the amount of signal data available to the classifier actually impacts its performance. Does more data help? Spoiler, usually yes.
So a bigger grid means more data points per signal.
Yeah, exactly. A larger matrix, like 64 by 64, means more information points per signal, which intuitively should help the AI make better distinctions. They also tested two crucial power ratios for the far and near users, PFPN, specifically setting this ratio to 2 and 4. This directly mimics different power allocation strategies, how much stronger the far user signal is compared to the near users. That ratio is a vital parameter in NOMA systems for managing interference and enabling S, so testing different values is critical.
And critically, they generated all this data across a broad and realistic range of SNR signal-to-noise ratio values. They went from a very noisy -10 dB all the way up to a very
when you multiply that out, 4 modulation types times 16 SNR levels times 10,000 signals per type, it results in a massive 640,000 individual signals. And remember, each of these signals is an M matrix of complex numbers, previously formatted for analysis. This extensive and incredibly varied data is absolutely fundamental for training robust and generalizable machine learning models. Models capable of handling the immense complexities of OTFS-NOMA in diverse real-world conditions. Honestly, without this meticulous and custom-generated dataset,
their machine learning experiment simply wouldn't be possible. Its creation is a landmark achievement in itself for this field.
Okay, so they have this truly massive and incredibly complex dataset tailor-made to this specific challenging problem. But machine learning algorithms, they don't just listen to raw data, do they? Especially not complex matrices of numbers like U and K below. They need it prepared, summarized, highlighted in a specific way they can understand. That brings us to data preprocessing and then feature extraction. It's essentially like cleaning, organizing, and maybe highlighting your notes before you start studying for a really critical exam. How did they prepare this complex way?
AOE signal, which remember is already the product of all those intricate transformations for the machine learning algorithms to actually learn from effectively.
That's exactly the right analogy. The first essential step in this process, the data preprocessing, is to take a complex YKL, signal an NXM matrix of complex numbers sitting in the delayed Doppler domain and break it down. Break it down into its fundamental real-valued components, which are easier for many standard ML algorithms to handle. So they extracted the in-phase component, which they labeled YI. This is simply the real part of each complex number in that HKL matrix. Then they extracted the quadrature phase component, YQ, which is the imaginary part of each complex number.
Both YI and YQ are themselves NXM matrices, essentially representing the horizontal and vertical coordinates, if you like, of the signal's complex path. Additionally, they derive the amplitude
and simplification is crucial because it provides the algorithms with more digestible, more interpretable inputs to work with.
Right, makes sense. Break it down into manageable parts. And once you have these three separate real valued components, the in-phase, quadrature, and amplitude matrices, that's when you embark on the feature extraction process. Correct. This is where you transform that, well, still fairly raw data into specific, meaningful insights or characteristics that the machine can actually learn from. It's almost like giving the machine a set of distinct visual cues or statistical summaries to look for, rather than just showing it the entire overwhelming picture. What kinds of features
did they cleverly pull out of these matrices? This seems like a really critical step.
Yes, feature extraction is absolutely where they distill the essence of the signal into quantifiable, learnable characteristics. It's where the intelligence starts to get encoded. They focused on two main categories of features, which is smart because each provides a different and complementary lens through which to view the data. It's a bit like analyzing a person by both their facial features and their personality traits. You get a fuller picture. First, they extracted statistical features. These are classic quantitative summaries derived from each of those three components. YI, YQ, and YA.
For each of these three components, they calculated a really comprehensive set of statistical measures: mean, median, mode, minima, maxima, channel range, kurtosis.
That's a robust set of 9 different statistical features for each of the 3 components, resulting in a total of 27 statistical features right there. And what's particularly fascinating here is how these relatively simple numeric summaries, like how spread out the data is, variance, symmetry, skewness, or the peakedness of its distribution, kurtosis, can provide so much discriminatory information about the underlying signal characteristics and, ultimately, its modulation type. They offer a quick high-level fingerprint of the signal.
Now, the second category is where their ingenuity truly shines, I think. They extracted image-based texture features.
Image-based? From a radius signal, how does that work?
Well, since YI, YQ, and YA are all NXM matrices, they can be conceptually treated as an image, just a grid of pixel values, right? This clever insight allows them to leverage powerful techniques developed for image processing and computer vision. Really neat application. From these images, they extracted 2 widely used types of texture features. The first is the local binary pattern, LBP histogram. Imagine looking at each pixel in the signal image and comparing its value to its immediate neighbors. LBP
essentially captures local texture patterns within the image by creating a binary code for each pixel based on whether its neighbors are brighter or darker, higher or lower value. This gives a rich description of the
co-occurrence matrix, GLCM, which basically counts how often different pairs of pixel values occur in the image at certain distances and angles from each other. This provides incredibly detailed information about the image's texture properties, like its coarseness, contrast, homogeneity, and regularity. Again, 5 hydraulic features were extracted for each of the 3 images. This gives an overall 30 image-related features, 5 LBP, plus 5 hydraulic, times 3 components. So by combining the 27 statistical features with these 30 ingenious image-based texture features, each of those
640,000 complex signals in their dataset was transformed into a concise yet powerful set of 57 numerical features. This is the streamlined, meaningful input that the machine learning algorithm
is incredibly clever at treating the signal components like images to extract texture features. So with the data meticulously pre-processed and these clever, multifaceted features extracted, it's finally time to teach the machines to listen and categorize, right? This is where the machine learning algorithms themselves come in. They're the brains of the operation, learning to recognize the patterns hidden within those 57 features. How did they approach training these models, and which specific algorithms did they choose to test for this absolutely crucial task of modulation classification?
Right, so with their massive, carefully curated data set, now represented by these 57 features per signal, they followed standard sound machine learning practice. They split the entire data set into distinct training and testing sets. They used a standard 80.20 ratio for training and testing. This meant a staggering 512,000 signals were dedicated solely to training the models, as well as the algorithms to learn the intricate relationships between those 57 features and the corresponding modulation types, BPSK, QPSK, APSK, 16QAM.
The remaining 128,000 completely separate signals were kept aside, untouched, strictly for testing the model's performance after training. This 80.20 split is
the decision tree classifier. This algorithm works like a classic flowchart, or, as the name suggests, a tree-like decision model. It learns by making a series of decisions or splits at each node based on the input features. At each step, it chooses the feature and threshold value that provide the most information gain, which essentially means it chooses the split that most effectively reduces the entropy or uncertainty about the class label, the modulation type. You can think of it like playing 20 questions at each step. A decision tree asks the question that gives it the most crucial
information, drastically narrowing down the possibilities until it hopefully pinpoints the correct modulation type. They're often praised for being relatively easy to interpret. Second,
printing the data off the table to separate it.
Exactly that kind of idea. Imagine you have red and blue marbles mixed on a flat table, and you can't draw a single straight line to separate them. And SVM is clever. It might mathematically lift those marbles into a third dimension, or higher dimensional feature space, and suddenly, in that new arrangement, you can easily slide a flat sheet of paper, a hyperplane, between them to perfectly separate red from blue. It then maps that clean separation back down to your original data. Pretty powerful stuff. Third, K nearest neighbors, KNN.
This is a relatively simple, conceptually straightforward algorithm. It's non-parametric and instance-based. When a new, unclassified signal comes in, represented by its 57 features,
it's a bit like predicting a new student's major based on the most common major among their K closest friends in the classroom. It relies entirely on proximity and similarity in the feature space. Simple, but can be effective. And finally, fourth, the random forest classifier, RSC. This is an incredibly popular and often very robust ensemble technique. Ensemble means it combines the predictions of multiple individual models to make a final decision. In this case, it combines multiple decision trees.
instead of relying on just a single, potentially flawed decision tree, it builds a whole forest of many decision trees, sometimes hundreds. Each individual tree in the forest is trained on different random subsets.
And decided by majority voting among all the trees in the forest. Whatever class most trees predict wins. What's truly fascinating here, and why it often works so well, is how RSC leverages the wisdom of crowd principle. By combining many diverse, slightly different decision makers with trees, it achieves far more robust, stable, and often significantly more accurate predictions than any single decision tree could achieve on its own. It's a very powerful technique.
Okay, so after all that meticulous preparation, the massive data set generation, the clever feature extraction, and training these four diverse machine learning models, we finally arrive at the big reveal.
The results. Yeah.
For this truly complex task of classifying modulation types in this unique OTFS-NOMA environment, which of these machine learning models actually performed the best, and, how well did it really do? Was it good enough?
Well, the results presented in the paper were actually quite clear and pretty compelling. They delivered a definitive winner. The findings show that the random forest classifier, RSC, consistently outperforms the other classification algorithms they tested. It wasn't even particularly close in many cases. If you look at figure 2 in the paper, which plots the overall classification accuracy against the signal-to-noise ratio, SNR, you can visually see the superiority quite dramatically. The line representing the RSC accuracy is always
Clearly at the top, and it rises sharply as the signal quality improves. What's even more impressive and really crucial for practical application is that its accuracy approaches its saturation.
It's not just good, it's a critical threshold, I'd argue. An accuracy of over 90% in this context is foundational. Why? Because remember that successive interference cancellation SIC process at the near user.
Right, where it has to decode and subtract the far user's signal.
Exactly. If the near user can't reliably identify the far user's modulation type with high accuracy, it can't perform that subtraction correctly. And if SIC fails, the entire NOMA process, which relies on successfully removing that interference to recover the
Weaker signal fundamentally breaks down. So without this high accuracy demonstrated by RFC, you'd be looking at constant data errors or even dropped connections for those stationary near users trying to show the same.
That's an excellent point about the link to SIC. It really demonstrates the practical viability of this approach, especially at those reasonable SNRs. But the paper also provides a much more granular and detailed performance analysis, looking across various scenarios like different signal lengths and power ratios, as presented in Table I, right? Can you break down why RFC seems to be consistently better across these
better in each case they tested. Let's look at some specifics to understand the drivers behind that performance. Okay, consider the baseline scenario they tested. This used a power ratio, PFPN, of 2 between the far and near user and the smaller signal length of 32 by 32. In this setup, RFC achieved an average accuracy of 66.34%. In comparison to the other three, KNN, SVM, and DTC were
all clustered together, described as quite similar, hovering around 56-57% accuracy. So even in this most basic lower data setup, the random forest classifier already
to an impressive 72.35%. This clearly demonstrates that, as the paper states, performance is improved because of increase in the input data size.
More data, better results. Makes sense.
Absolutely. Intuitively, having more data points within each signal, going from roughly 1,000 points to over 4,000, provides more information for the algorithms to learn from. It allows them to extract more reliable features and make more accurate classifications. It's like having a much higher resolution image to analyze. You can see finer details. They also rigorously investigate the impact of power ratio, another key NOMA parameter. What happens when you increase the power ratio, PFPN, from 2 up to 4? This means the far user signal is even stronger relative to the near user signal.
The finding was that, with increased power ratio, all the algorithms exhibit improved accuracy for the same sample size. Everybody did better. For example, focusing on RFC again, at the
beneficial for the subsequent SIC process we discussed. A stronger target signal is always easier to decode first. So putting it all together, the overall best performance observed across any of the tested algorithms and scenarios was attained by, unsurprisingly, the random forest classifier. It achieved the highest average accuracy of 74.67%. And this peak performance occurred under the condition where PFPN equals 4 and N equals M64. This represents the most favorable conditions they tested, maximum signal data and ambulance of 64, and the larger power separation, PFPN4.
This comprehensive analysis across different conditions truly demonstrates the consistent superiority of the RSC model, making it the clear standout choice for this specific, challenging application.
That's a really great overview of the successes, strongly confirming RSC's strength across the board. But machine learning models, as we know, they aren't perfect, especially when the signal quality drops, right? Where does the model tend to struggle? And maybe more interestingly, how does it struggle? The paper very wisely uses confusion matrices in Figure 3. These are great because they show not just if the model is right or wrong, but how it's wrong, which specific modulation types does it confuse with others. What key insights do those matrices give us about the
classifier's limitations and perhaps its remaining strengths?
Ah, yes, the confusion matrices. They are absolutely critical because they offer an incredibly nuanced view into the classifier's actual behavior.
Modulation. That's excellent.
Why is BPSK so easy for it? Well, BPSK is the simplest modulation here. It only uses 2 distinct constellation points, essentially, 2 signal patterns to represent data bits, 0 and 1. These points are very far apart in the signal space, making them relatively easy to distinguish even with some noise. However, you'll immediately notice a significant dip in accuracy for the higher order modulations like QPSK, 8PSK, and 16QAM. The paper notes this is due to some similar constellation points in these schemes. Their constellation points are packed much closer together, so the
classification accuracy for these is relatively low when averaged across all SNRs, especially dragged down by performance at low SNRs. This means when the signal quality is poor, low SNR.
which has 4 constellations. oscillation points. It's only 64% accurate at 60 dB. A significant portion, about 34%, of QPSK signals are mistakenly classified as APSK, which is 8 points. This confirms that these moderate SNRs, distinguishing between these denser modulations, particularly those like QPSK and APSK, that show a similar structural arrangement of their symbols, remains a definite challenge. The points are still too close together relative to the noise level, and misclassifying these can lead to serious data errors downstream in the SIC process, potentially impacting the reliability of the whole NOMA system.
But this is where it gets really interesting. Figure 3C shows the confusion matrix at 10 dB SNR. Now we're getting into better signal quality, and the performance jumps dramatically, right across the board for all modulation types.
As the noise decreases and the signal becomes much clearer, the distinguishing features of each modulation type, captured by those 57 features, become far more apparent to the classifier, leading to near-perfect identification in many cases. This also carries a really positive implication. For real-world scenarios where maintaining a minimum SNR around 10 dB or higher is feasible, this RFC-based AMC system can perform exceptionally well, enabling reliable OTFS-NOMA operation.
It is remarkable how much just a few dB of extra signal quality can enhance the classifier's performance, taking it from really struggling with some types to near perfection with a huge insight. Finally, Figure 4 in the paper visually summarizes the overall trends. It plugs SNR versus accuracy specifically for the winning random forest classifier, but across those different scenarios of signal length, NM, and power ratio, PFPN. What are the key takeaways or patterns we can see from this comprehensive visualization of RFC strength under various conditions?
Yeah, Figure 4 provides that holistic, compelling visual narrative of the RFC's performance across its entire operational landscape as tested. The most immediately striking observation looking at that graph is that the line representing the PSPN4 and 64 by 64 configuration is consistently at the very top. Right across the entire range of SNRs they tested, from negative 10 dB to 20 dB, this visually confirms what table I suggested numerically. This setup combining the higher power ratio means that our user signal is more dominant
And distinct, and the larger signal length, providing more data points, provides the absolute best classification performance for the RFC. That's clearly the sweet spot for maximizing accuracy. More generally, looking at the
It certainly seems so. This strongly reinforces the earlier finding that a larger signal length, essentially providing more data points per signal sample, profoundly helps the classifier achieve better accuracy, regardless of how the power is split between the users. It strongly suggests that the richer detail contained within those larger signal samples gives the AI more robust information to discern the subtle differences between the modulation types, especially when noise is present. We also observe the trend regarding power ratio. Higher power ratios,
specifically PFPN4, generally yield higher accuracy than the lower ratio, PFPN2. This makes intuitive sense, as we discussed. A greater power disparity makes the target far usable.
achieving the same classification accuracy. This might suggest that when the noise is that dominant, the subtle difference in power allocation has less of an impact on the overall accuracy. Noise is just overwhelming everything else. But beyond that specific noisy region, a larger power disparity generally tends to improve classification accuracy. Overall, these findings confirm the robustness and superior performance of the RFC, especially under optimized conditions like higher signal lengths and power ratios. And importantly, they provide critical guidelines for engineers designing future OTFS-NOMA systems where accurate
Modulation classification is paramount for success. Hashtag outro video.
And there you have it. We've really embarked on a fascinating journey today, deep into the world of cutting-edge wireless communication. We've explored how this powerful combination of OTFS-NOMA provides a really promising dual-pronged solution for future wireless networks that need to seamlessly handle users with incredibly diverse mobility profiles, everything from those high-speed drones zipping around down to static smart home devices just sitting there. And critically, we've seen how intelligent machine learning, specifically the robust random forest classifier.
In this study can reliably and automatically identify the different signal types being used in this complex multi-layered environment. And this capability, this AMC, it isn't just some academic
This kind of work lays the fundamental groundwork for the next generation of wireless networks. Networks that will inevitably touch every aspect of our increasingly connected lives. Imagine a future where you have smart city infrastructure, your autonomous vehicles navigating bustling streets, your remote-controlled agricultural drones tending fields, and all your personal devices. All communicate flawlessly, instantly, and reliably, no matter their speed or location, efficiently sharing the same limited spectrum without a hitch. This research is fundamentally about making our connected world not just faster, but profoundly more efficient, more reliable, and ultimately more seamlessly integrated than ever before. It's about building the intelligent, adaptive...
Absolutely, and this really is just the beginning of exploring this intersection. The paper itself points towards future work. It suggests one possible extension of this work is to explore deep learning models, which may provide superior performance. Deep learning, with its ability to automatically learn complex features directly from vast amounts of data, could potentially push that classification accuracy even higher, maybe handle even noisier conditions or more complex scenarios. It also suggests potentially increasing the number of
modulations while generating the data set, meaning teaching the AI to classify an even wider, perhaps more complex, array of signal types that might be used in future systems. And this raises a really important question.
How much more sophisticated will these AI-driven classification systems, these intelligent ears of a network, need to become just to keep pace with that relentless demand? And while other fascinating, perhaps unforeseen challenges and opportunities will emerge at this critical intersection of wireless communication and artificial intelligence, it's a field that's really just getting started, and honestly, its implications are truly limitless for how